Hi there! Before we change gears, let's see some other powerful applications of this method that was derived from Hamilton's principle and the idea of the extreme of a function. Let's start talking about optics. Let's consider a beam of light traveling in a medium. Light travels at a speed v equals to z over n, where c is the speed of light in a vacuum and n is the refraction index of that medium. This velocity v is ds over dt, where s is the distance traveled over the path light takes. I am not making any assumption on the path light follows. I can solve for dt and integrate over the path from its initial position until its final position. This way, I get the time that light is traveling. Let me consider this a two-dimensional problem just for simplicity. Then I can write the differential of s as the square root of the differential along x squared plus the differential along y squared. Fermat's principle states that light travels in a path that takes the least amount of time. So this integral has to be minimum. Now is when I am going to use results introduced some videos ago. The formalism developed by Euler and Lagrange, and for the action in that case, is in fact more general than we have used so far. S equal to the integral of L dt works for any function L, not need to be k minus u, or have to do anything with mechanics or even physics, and dt doesn't need to be time. All that is required is that the function L depends on the quantities q, q dot, and t, where x can depend on the parameter t. That said, let's go back to the beam of light. I want to minimize t, this integral, but I can write the integrand in terms of the quantity x, as this is square 1v dx, where dy over dx is the derivative of the quantity y with respect to the parameter x, which I'll call y prime. So now I have the integral of this function I will call f, which depends on y prime, the derivative of y with respect to x. Here the parameter x plays the role of time in Euler-Lagrange, and y prime plays the role of velocity. And this function inside the integral plays the role of the Lagrangian. So now it is time to apply Euler's Lagrange to this function f. This first term is 0, and this second term says that this derivative is 0. Now I'll make a change of variables, y prime equal to the tangent of theta. This has to be constant. I can rearrange things a little bit and get that n times the sine of theta is constant. But this is just Snell's law. This says that the angle is constant, which means that the trajectory is a straight line. Well, so long as light does not change of medium. If it does change of medium, then the angle changes but remains constant in the new medium, which is refraction of light. In the next video we will see another application of this. May the science be with you.